And we're ready to go. So reminder that your test 3, is on Monday. And the PowerPoint we're going to finish up right here in the morning. It's the last material on your test. Test 3 is going to be much similar to test 2. I'll let you have whatever you want. Again, my only thing I'll say is don't put my test online. Don't ask other people to help you. Don't take pictures of my test. Don't take screenshots of my test. Otherwise, you can use your notes. You can ask Google if you want, but I'm going to make sure that if you Google my questions, you're not going to get anything helpful. So don't rely on that. Make sure that you can do the problems in a timely manner, or if you try to search for everything on Google or on through your notes, you're not going to have time to finish. So make sure you're organized going in and make sure you know how to do the problems going in. Don't expect to be able to just go in there, look back at your notes and figure out how to do it on the fly. That didn't work out for people on test 2 and probably won't work out for people on test 3. All right, so with that, let's continue on with what we were doing. So on Monday, we finished with this problem using Hess's law to determine delta H's of reactions by multiplying reactions, by switching the reactants and products of a reaction, and by combining reactions. So this was all about Hess's law. And we're going to continue just a little bit with delta H here. And let's talk about standard states to begin with. So in chemistry, to make calculations simple, we can decide that matter has a standard state. That is, we define it's in its natural standard conditions if you're a gas and you're at 1 atmosphere of pressure. If you're a solid or liquid in your stable form at 1 atmosphere and a certain temperature, usually we say 25 C. Or if you're in a solution, your concentration is 1 molar. And so we use these standard states for ease in calculations, where we usually say, you know, if you're in your standard state, your enthalpy is 0. It's just a way for us to set a baseline. And what we can do with that is start to do some interesting calculations. One thing we can do is, what is the enthalpy change in a reaction if everything is at its standard state? So let's look at the symbol delta H naught. So delta change, always remember final minus initial. H is enthalpy or heat, and this naught standard state. When we have this symbol, this says we're calculating the enthalpy change if everything is in its standard state, right? So that's what that little symbol means. And standard state conditions, again, are up here. We can also calculate how much energy you gain or lose, the standard enthalpy of formation, when you create something. So this F is just stand for formation. So if I'm making 1 mole of a pure compound from elements, how much heat is released or how much heat is absorbed to create that 1 mole of products? That's what standard enthalpy of formation is telling us. As we have the naught as well, we have to be in standard state. And if we're looking at pure elements in standard state, formation of that is always 0. Again, that is just something chemists have decided to say, well, that's going to be our baseline, our 0. And that allows us to do other calculations. So that's what we're going to work on to begin with here. Standard enthalpy changes and enthalpies of formations. And to calculate a standard enthalpy change of a reaction, here is the actual equation for us. So let's read this equation out in English, right? The change in enthalpy in standard state for a reaction is equal to the sum. Remember that giant sigma means you're adding all of this together. N moles. So the sum of the number of moles multiply whatever the change in enthalpy of formation at standard state for your products are, minus the sum of moles multiplied by delta H formation of your reactants. So I know there's a lot of symbols here, and it probably doesn't make too much sense looking at this in the abstract. But we're actually going to put numbers here to start and understand what some of this means. Delta H formation, these are just constants, and every element, every compound has a different value here. And that's what Appendix 2B means. If you go in the back of your book or back of a lot of chemistry textbooks, you'll just find lists and lists and lists of delta H formation. And so that's where we pick up those values from. Someone has a mic on. Huh. I will mute everyone then. Okay, everyone should be muted now. Usually that happens automatically. So let's actually look at how to use this equation then. So question 6, I will do A here. Write an equation for the formation of the compounds from the elements in their standard states and find delta H naught F, or the standard enthalpy change of formation for each reaction. So NO2. And this list here, these are delta H Fs of different compounds. So when doing this, the first thing you want to do is write a chemical equation for the formation of each compound. So for A, I'm just going to write the product, right? So I'm trying to form NO2. So my product is going to be NO2. And I need to create that from the elements that make up NO2. And NO2 is made out of 2 elements, right? Nitrogen and oxygen. And in the pure state, which is given here, these are the pure states of some elements. Nitrogen is always N2. Oxygen's O2. So to make this reaction, it's nitrogen, but it has to be N2 because that's the standard state, plus oxygen, gas, 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 make NO2. So that's our reaction. We're not quite done yet with the reaction because it's not balanced. And for formations, this is going to be something different than what we've done so far. When you're doing formation reactions, which is what we're doing here. When you're calculating delta H of formations, usually the product you want to keep as 1 mole, which means you get to do some interesting stuff. To balance this, I have 2 oxygens on the right, 2 oxygens on the left. That's fine. 1 nitrogen on the right, 2 on the left. That's not fine. And any other chemical reaction, you would put a 2 in front of the NO2 and then balance out the oxygens. However, like I said, this is going to stay at 1. Therefore, this is one of the rare times in chemistry where you can use fractions to balance out an equation. Almost any other time when you're balancing out an equation, you are not allowed to use fractions. Here we are because we're doing formation reaction. So the balance reaction is 1/2 N2 plus O2 goes to 1 NO2. And now the actual math for that. Delta H formation at the standard state equals the number of moles of our products, 1, multiplied by the delta H of formation of our product, which is NO2, which in this table is 33.2, minus, now I'm putting a bracket here because it's sum of reactants, 1/2 number of moles multiplied by the delta H of formation of N2, which is 0, plus, so this is the N2 portion, this is NO2, this is the O2, plus 1 for 1 mole of oxygen, multiplied by the delta H of formation for oxygen, which is 0. So 1/2 times 0 is 0, plus 1 times 0 is 0. So the delta H of formation for N2 is actually 33.2, which is what it says here in the table. But I want people to get practice with writing out the equation. Then I want you to get practice, or writing out the chemical equation, then get practice using the mathematical equation. So that's what we're going to start with here. Why can't we just balance it like normal? Because we are creating NO2, right? Since you're doing a formation, you want to know how much heat is released or absorbed for every 1 mole of NO2 that you make. So that's in the definition of this problem. You're making 1 mole of NO2. Therefore, you have to keep it as 1 mole of NO2. If you made NO2 2, your delta H of formation would be 33.2 times 2, because you would have 2 moles of it, which would be 66.4, which is incorrect, because you would be saying you have to absorb 66 kilojoules of heat to make 1 mole of NO2. So keep in mind, delta H formation, you're making 1 mole of product. That is the definition of that. Well, there's more practice. So try to do BC and D with following along how I did A. If you get stuck, have questions while doing this, let me know. Otherwise, I'm going to give you like 3 to 5 minutes in doing B, C, and D. Write down the chemical equation and then write down the mathematical equation. And let me know if you have questions while doing this. So question is, do we have to figure out how to get O2 to O3? Yeah, it's what do you multiply O2 by to make sure there's 3 oxygens instead of 2? So another question, the first problem when plugging in numbers for the formation chart, do we always need to put the products first and the reactants? Yes. This reaction for delta H formation is always products minus reactants. Usually anytime you see a delta, it's final minus initial. Here, our final states are products and our initial states are our reactants. So that's why it's products minus reactants. Basically, rule of thumb, anytime you see delta in chemistry, it's final minus initial. So we'll do like a minute or two more before I dive in. All right, let's take a look at B here. So I'm making MgCO3. That's my product. And it's made out of 3 things, Mg, C, and O. Oops, that's just, let me erase that. MgCO3 solid. Right. So it's made out of Mg solid plus carbon solid plus oxygen gas. It's O2 because that is the standard state of oxygen. Balancing the 2 oxygens on the left, 3 on the right. So if I do 3 halves O2 is 3 oxygen. So that's a balanced equation now. And my delta H formation, products minus reactants. So 1 mole of MgCO3 multiplied by the delta H formation of MgCO3, negative 1095.8 minus, now my products, 1 times mg, which is 0, plus 1 times c, which is 0, plus 3/2 O2, which is 0. So it just equals negative 1095.8. And I understand that doing this all 0, 0, 0 stuff seems redundant right now, and you might not see the point of it. The reason why I'm having you write it out like this, because in the next problem we do, these all won't be zeros. They're actually going to be numbers. So I want you to get the math formula down in your head of how to do this. So C2H4 is our product. It's gas made out of carbon and hydrogen, carbon solid. So we need 2 of those to balance, plus H2 gas. We need 2 of those, delta H formation. So I'll go through it again. So products minus reactants, 1 mole of C2H4 multiplied by the delta HF of C2H4 minus 2 for carbon, because we have 2 moles, multiplied delta H of carbon, 0, plus, because they're on the same side, so they get a plus, 2 for 2 moles of H2, multiplied by the delta HF of H2, 0, so 52.4. And that's not surprising because these values are delta H formations already, and I'm telling you to calculate it. So it should be the same number. D, CH3OH, liquid. Now a carbon, hydrogen, oxygen, carbon, 1 mole, so we're good. Oxygen, it's 2, so I need 1/2 of that. Plus, there's 4 hydrogens. So to do delta H of this, 1 mole CH3OH is 1 times delta HF of CH3OH, negative 238.6 minus, because now we're going to the reactants, 1 mole of carbon times 0 plus 1/2 mole of oxygen times 0 plus 2 times delta H of hydrogen, 0. So negative 238.6. So that's the setup for these types of problems. What are you making? What's it made out of? Make sure everything's balanced. And then it's products minus reactants. So any questions about these types of delta H formation problems? Is the answer always going to be the value of the product? No, it is not. We'll see that in the next problem. This is the simplified version of these types of problems, because we're making it from elements in their standard states, and elements in their standard states like nitrogen, oxygen, magnesium, carbon, hydrogen, delta H formation in the standard state of an element is always 0. In a compound, it's not 0, but in an element, it is 0. So that's why it's always, all the reactants are 0. So we're going to look at cases where it's not 0. And that is when we are doing delta H reactions, right? If I want to know how much heat I have to put into a reaction or how much heat is lost in a reaction, that's what I'm doing here. So this symbol really means how much heat was lost or gained during a reaction. And I need the delta H formation delta H formation numbers that we get from a table to calculate this. But the math is exactly 100% the same, right? So I've already balanced out these equations for you, so we don't have to do anything there. So let's see how we do this, and we're going to do it for A. So I want to know for the reaction in A, what is delta H reaction? How much heat was lost or gained? So it's products first because it's delta. So I have 1 mole of C2H6. From my table, the delta H of formation of C2H6 is negative 84.68 kilojoules per mole. So that's 1 times 84.68, negative 84.68, minus, because it's always products minus reactants. So let me just draw this out. C2H6. This is C2H4. Minus 1 mole of C2H4. The delta H of C2H4 is 52.4. So 1 times 52.4. Plus, I have this addition sign because we are dealing with reactants. So everything on the same side of the arrow gets a plus. Plus hydrogen, 1 mole, times the delta H of formation of hydrogen. H2 is standard state, so that's 0. So this is really negative 84.68 minus 52.4. Let me get out Excel. 84.68 minus 52.4. So the delta H reaction for this equation is negative 137.1 kilojoules per mole. The second parenthesis, so this equation, delta H reaction, is N number of moles, delta H formation, and it's the sum of, for every product you have, minus sum of number of moles, delta H formation reactants. So this parenthesis says 1 times 52.4 plus 1 times 0. These are all my reactants. These are my products. Right, I have 2 reactants, C2H4 and hydrogen, so I need to add their values together. That's why I have a parenthesis there. Yep. All right. Try to figure out the other values. What is delta H reaction for B, C, and D? We'll do about 1 more minute before I jump back in there. All right. So same exact math as the last problem. Same way to set up the math, that is. So B, products minus reactants. So 1 mole of H2, and H2's delta H of formation is 0. So 1 times 0 plus second element CO2. So 1 mole of CO2, delta H formation of CO2 is negative 393.5. So that's all our products. Now minus our reactants, 1 mole of carbon monoxide, which has a delta H of negative 110.5. So 1 times negative 110.5. Whoops, did not mean to put the parenthesis there yet because I need to do an addition plus H2O gas. So 1 mole of H2O gas multiplied by, there it is, the delta H formation of H2O gas, which is negative 241.8, close parenthesis. So that's the mathematical equation. And that should be negative 745.5 kilojoules per mole. No, it should not, because I put a plus sign instead of a minus sign. That should be negative 41.5 kilojoules per mole. So that is how much heat is released when you make hydrogen gas and carbon dioxide gas from combining carbon monoxide gas and water vapor. Negative 41.5 kilojoules per mole. Let's go on to C then. I'm going to put C right above B. C. So 2 moles of HNO3. HNO3 is negative 207. So 2 times negative 207 plus nitrogen monoxide. 1 mole of nitrogen monoxide multiplied by delta H formation, 91.3. Those are my products. So N parenthesis minus, now my other parenthesis for my reactants, 3 moles of NO2. So 3 times delta H of formation of NO2. Whoops, did not mean to put the dash there. 33.2. I'm just doing dashes on the equation to keep track of which ones I already put into my math. So that's why I have the dashes right there. So 3 times 33.2 plus, because we're still dealing with reactants, 1 mole of liquid water. The delta H formation of liquid water is negative 285.5. And that should be negative 136.8 kilojoules per mole. Finally, D. I'm going to erase A down here. All right. D is going to be the same exact thing. So start with the products. 2 moles of chromium solid. Well, chromium solid is the standard state of chromium, so that's 0. Plus 3 moles of carbon dioxide gas. Carbon dioxide gas is negative 393.5. End parenthesis, because that's my last product. Whoops, that should be a 3 times that. Oh, I do have 3 times negative 393.5. Yep. Okay. Minus chromium oxide, Cr2O3, 1 mole times negative 1139.7 plus 3 moles of carbon monoxide. So 3 times negative 110.5. In parenthesis, do that calculation. And when I did that calculation, I got 290.7 kilojoules per mole. How do I enter B in the or can I? Oh, you got it. Yeah, parentheses are your friend here. Otherwise, the order of operations might get wonky. Well, they'll definitely get wrong if you don't have parentheses. What I also like to do, because I'm really neurotic about calculators, what I actually do is I have double parentheses. So I have like 1 times negative 110.5. That's in its own parenthesis, plus 1 times negative 241.8. That's in its own parenthesis, and that's in one big parenthesis. That will make sure 100% the order of operations are following what I want it to follow. All right. So questions about how to calculate the standard change in enthalpy of a reaction. Delta H not reaction. You want to have confusions, questions? So question on the test, will we have these references or will we need them in our notes? I will most likely I'll probably just give you a table if I give you a question like this. So it's not something you'll need to write down because it's just a reference page anyways. So I'll likely provide you with values. I might provide you with more values than you will need, and you'll have to decide which values you'll have to use from what I provide you, but they'll be provided, yeah. The formations given on the slide, are those the only ones you will ever use? No, there are about, well, for every single element and compound, there's a value for this. And then if you look at the back of your book, there's about 500 given, and that's just a short list. So no, but like I said, if you need to use it on an equation, I will give you delta H formations. All right. So I know this looks like, especially when you see all the numbers out there, it looks like a lot, but it's just the same thing over and over and over again, right? How many moles of a molecule do you have times the delta H formation? And you always do products minus reactants. Make sure you all add your products together. Make sure you add all your reactants together. Right. So we do have a couple minutes. So I just want to introduce our next PowerPoint, which should be in the test 4 folder. So let me pop that up really quick here. And we're going to get away from math for a little bit. So, yay. And we're going to talk about light. And light is radiation. It's a type of radiation, and it's called an electromagnetic radiation because light is made out of like two different properties, electricity and magnetism. They combine together to make light. And depending on how you measure light, it's really weird, but you either see light as a wave or you see light as a packet of energy. From here on, we are on test 4. Yep, this is all test 4. This PowerPoint on is test 4. And so we can either think of light as a wave or a packet of energy. It's both, but it just depends on how you're measuring it. It's what you see. So when we measure the waves of light, they move at a constant speed, which is called the speed of light. 3 times 10 to the power 8 meters per second, which is incredibly fast. It's ridiculously fast. That's why you can see something long before you hear it, because sound travels at like 500 meters per second. Sound is super slow. So to understand waves, we need some terms to describe a wave. So the terminology we have is amplitude. That is, how high does my wave go up? Wavelength, which is given this symbol. What is the distance between peaks? And frequency, which is given this symbol. It looks like a V. It's not, it's Greek, but you can call it V. This symbol, by the way, is called lambda. So that's lambda. I believe this is nu. Don't quote me on that. I'm not too good on my Greek, but I just usually call it V. Frequency is if you look at a given point, how many waves pass that point in a given time. So if you are standing right here, and you had a stopwatch, and you press the stopwatch, and just mark off a set amount of time. Frequency is just how many times the wave passes that point. And wavelength and frequency are inversely proportional, right? The longer your wave is, the longer the wavelength, the lower the frequency, the lower that it will pass through that point. But if your wavelength is really close together, your waves are really close together, like that, then frequency would be very high. And so we can convert between the frequency of light and the wavelength of light through this nifty equation. Frequency equals speed of light divided by wavelength, or wavelength equals speed of light divided by frequency, or the wavelength times the frequency equals speed of light. All right, so that was just my little introduction. On Friday, this PowerPoint I put up today probably doesn't take that long to do, as it's really introduction slides. So we're going to look at light. We're going to talk about Einstein, see why he won the Nobel Prize. And it wasn't for his unifying theory of physics. It was because he figured out that light is packets. That's why he got his little prize. Well, not little prize. That's why he got his massive prize. But that's what we'll talk about on Friday. This is all test 4. But with that, we are out of time. So if you have questions, especially relating to test 3, if you're going over the test 3 material, you don't know how to do something, let me know. I can help. Most likely I can help. So contact me. I'll put up a homework that will go over the delta H of formation stuff that we did today. That stuff will be due next week, Wednesday. So it'll be due after your test. I do suggest you try it though, because you're going to have questions about delta H formation on your test. So make sure you know how to do those. Otherwise, I don't think I have anything left for you. So thank you for stopping by. Hopefully I will see you on Friday. And right, and have a good day, everybody. Take care.